Back again. We now move to the second part of the short course.
Thank you very much. Thank you. Hi, thank you very much. Okay, then let's indeed move to the practical part. So, well, what we will try to do will be to try to install the code and run a first simulations. So, well, to go to the, it's okay. So to go to the code website, this is not very clear to see, but what it says, I will write it down. This is a whiteboard, right? So you can go to this website if you are if you would like to download the code to your computer. And I will show you how to install it and how to run a first simulation. So if you can feel free to do it alongside with me with your laptop. And actually maybe that is better, because if you encounter any problems, we will be able to solve them during this session. Otherwise, if you want, you can also see what we do and try to reproduce it later, let's say at home. And if you find any problem, we can also talk about it tomorrow. So now, if you go to this website, there will be a section on documentation. And here there is, you can have access to several materials. So you can access the full documentation of the code here. This is written in a very old style, because, well, we inherited this from long ago, and we haven't improved it. But here, there is first a section on getting started, and we haven't improved it. So the instructions that are here are meant to be for Linux. First a section on getting started. But so in general, I would recommend that you run this on Linux. So if you have access to a cluster or so, you will generally use Linux. So my recommendation, if you don't use Linux, is learn how to use Linux. But in the event that you are using Windows or Mac, there are also some instructions. So for the case of Windows, you can follow this link. And here there are some instructions on how to create a virtual machine in your Windows computer in order to run back in the virtual machine. So this tutorial is given in English and Spanish, because I gave this for a course at a university in Mexico, but and the Spanish version is first. But if you scroll down sufficiently, you will see a version in English. So here there are the instructions in English. Unfortunately, I'm sorry to say that I don't know enough Portuguese to write instruction in Portuguese, but if I knew, I would be very happy to. Unfortunately, I'm sorry to say that I don't know enough Portuguese to write instructions. So these are the instructions to set up the virtual machine in Linux and set up the environment. in case you are using Mac, the instructions are very similar to those for Linux, because also the Mac OS operating system is very similar to Linux. Also, the terminal works in very similar way. The only differences is that instead of using the file bashrc, that is the one where contains all the commands that are executed when you start a new terminal, you will need to use the file set #rc, which is the same but for the Mac OS system. Also, for compiling the code, for installing and compiling the code, one has to use a Fortran compiler that is not provided by default in Mac, and then you need to install one. You also need to have MPI, that is the message passing interface that you need to run in parallel. That is also not installed by default on the Mac, also not in Linux, but it's very easy to install it. But in order that you don't have to go through these complications, Juan José Saldívar, a student from UNAM in Mexico, prepared a Conda environment that you can just load and have everything that you need in order to run back. And he has tested that in his own Mac. I don't have a Mac, so I didn't test this, but in principle this should work. So I don't have a Mac, so I didn't test this, but in principle this should work. I was supposed to add this to this instructions, but apparently I didn't. So if one needs this file, I can upload it. Perhaps I can do this at the end of the tutorial if that is okay for you. I can upload it. So, well, we will see first how to download the code. So, well, we will see first how to download the code. So, if I speak without the microphone, do you understand me well? Well, we will see first. Yes, because maybe I will turn the microphone off, because it is hard for me to type and have it here. So may I give it back to you? Thank you very much. It is hard for me to type and have it here. So may I give it back to you? Actually, let me add here the contents of the content environment of the file, just so that if you want to start using it, I will put it here. You should be able to access it in the website. well, first you have to have Conda installed, and so once you have it, you can follow the instructions that are in this same file. So that you can save the file as with this name, back underscore m.yml, and once you save that file like that, right. So now if you go to the website, you will see these contents of this file. So you should save it in this with this name, and then you should simply follow these instructions. So once you have followed these instructions, you will be able to follow exactly the same steps as in the tutorial that I will show you now. Okay, so downloading the code is very easy. You can get just execute this line in your computer if you have it, or you can go to the repository that is here. Or you can go to the repository. When the connection is a bit slow, but you can go and get directly from the repository. So of course I already have it installed in my computer, but I will show you how to as if I install it anew. So first I need to create a directory where I will put it. For example, I can create a directory with list of codes. I can go into this directory, edit codes. So now the directory is empty. So there is nothing in the directory, and then I will clone the source code for back from it. I simply execute this line. So now it is cloning it. Okay, we are in the codes folder and we have already downloaded back. So now we will install it. So the idea of back is to, or one of the design choices, let's say, was to keep all of the binary, all of the source code in one directory and keep every problem set up in a separate directory so that the user only has to modify what is relevant for the particular test case. So what we will do is to create a different directory and try to compile back in that other directory. What we will do is to create a different directory and try to but before this, we need to tell the system where to find the source code of back. In order to do this, we will edit the bash RC file that as I mentioned, is the file that tells the computer what to do every time that one opens a new terminal. So we will open the file that is called bash RC. So Vim, well, the Vim is just my editor. You can open it with whatever editor you have or you prefer. Let's say with Vim, with V, with Nano or whatever you prefer. So we can go here to the end, and we need to add this line. So in my case, I already have a line that tells the system where the back directory is. But in this case, I will comment it out, and I will use the one that of the location where I just installed it. So so in this case, it is this path. So I can enter here again. So I can and add this here. So we will export and add the environment variable will be called backdir. All of this is just common, called backdir. And I put back inside the code directory. So here I will write back like this. So you should replace all of this by the name of the directory where you have downloaded the code. So now that I have done this, I need to source the bash RC file. This is something that I just need to do once, only this time, because then every time that a new terminal will open, it will assign the value of the environment variable back here. So it is this. If I now ask for the value of that environment variable, so if I now ask for the it will give me the directory where I told you. Okay, and so as mentioned before, in case you are using a Mac OS, instead of editing bash RC, you need to edit set shrc, which is the equivalent in Mac. Now, okay, so with this we have installed the code in our system. Now let's try to run a first simulation. Okay, so with this we have installed the code in our system. Now let's try to run a first. So as I mentioned command lines that are here in the tutorial. So, well, now that I got into this directory, to have a fair simulation setup, I will take one from the examples that are provided in the code. I will show you what examples are there. So, if we go back here, and go to text, then RMHD. This stands for relativistic MHD. It's a RMHD. So we can see that there are these possibilities. This blue is still very bad. I will try to change it to something different. I hope this is better. So, well, as you can see, there are different setups. This one is to be torus, commissar torus, etc. And we will take the simplest of them, that is called shock tube. A shock tube is just something like what we explained before, that was the Riemann problem. You have two piecewise constant states that are separated by an interface. And then we will copy this example setup into the current directory. Now we have here a directory that is called shock tube, and we will get inside it. Now we have here a directory that is called shock tube, and we will get inside it. If we look at what is inside, you can see that there are different parameter files that are these .pal files that correspond to cases in 1D, 2D, and 3D. And there is also user file, amr.user.d, that contains the initial condition and everything that you need to set up as a user, and a few other things. But this is mainly the most important thing that you should have. So now that we are here in this directory, we will copy this line. And this line will tell back how to compile. We'll select some options that are independent from the parameter file, and we want our problem setup to happen. So the way it works is that it will call this setup.ps that is written in Perl. Also maybe a bit old-fashioned. We will improve on that at some point. It has then this -d stands for the dimensions and directions. So dimensions is the dimensions of the problem, and directions is the number of components of vectors. So we have one-dimensional problem with 3 vector components. Then these lines are relevant for spherical simulations, but in spherical coordinates, but not relevant now. Then this -g tells the total size of the AMR blocks of adaptive mesh refinement. Here we select the type of physics because there are several different kinds. In this case, we choose relativistic MHD, but there is in principle also resistive MHD and also other different options for physics. The equation of state, here gamma stands for the equation of state of ideal fluid, and here it also says architecture, G-Fortran, coordinate Cartesian. So here, because this tutorial is a bit odd, important, but there was an important change from G-Fortran to in G-Fortran after version 10, so that now it launches some error messages that previously it didn't care about. So instead of using architecture G-Fortran, we will use architecture G-Fortran 10, that is for G-Fortran 10 or later. So now we execute this, and now now that we executed this, it should change the make file. It didn't change anything because it was already what was supposed to be, but normally every time that you change the dimensions or something in the program, you should execute this line. So now that we have configured the code, we can simply type make. So now that we have configured the code, we can simply do make, and now it is compiling. And now it will take some time to compile. In the meantime, I don't know if there are any questions. In the meantime, I don't know if there are any. Well, you can find more information on. Sorry. This is the fastest one to run, just this is the smallest.
Oh.
And also the simplest. And okay, it has finished, so it didn't take us as long as I expected. So now that it has run, you will see that there is another file that has appeared that is called back. So that is our executable. And then in order to run the code, we need to create an output directory to put there the outputs. And to run the code, we can just copy this line. So this will simply ask MPI to execute the executable back with 4 CPUs. So if you want to execute in different numbers of CPUs, you change this number. It is telling to read the parameter file AMR back 1D, that is for a 1D simulation, and to write the output in this output file. Here, perhaps let's remove this part just to look at the standard output. So if we run this, well, it was very fast. So, but if you succeeded up to this part, you can run your first simulation with back. So just looking quickly at this standard output. So when it has a header, then it gives you some information on the parameters that were chosen. Then it gives you some information on the metric that was chosen, which components are 0 and what is non-zero. And then it gives information on the variables that are contained in the output file. And finally, some information on how long it took into the different stages. So I think, well, because the time is almost over, I will not go into how to visualize this output, but this is something that we can have a look tomorrow. However, if you want to start trying it yourself, this is what is contained will try something else. We will try how to run a total simulation. So here it is slightly different, but here you can compute the mass accretion rate, have a look at it, and also have a look at how increasing the resolution improves the way you resolve the turbulence. And so, well, the time is running out, so this will be all from my side today, and we will continue tomorrow. Thank you very much.
So we have time for questions. So questions can also be made along the event. So we are now moving to the lunch break, and we see you in the afternoon. Thank you very much. Let's thank the speaker again. Thank you very much. Let's thank the speaker again.